The final topic in chapter 4 is titrations, and titrations can have different varieties, but we're going to focus in on an acid-base titration. Again, we're running a reaction that we now recognize how to actually execute an acid-base neutralization, and we're going to be using our conversion factor skills to learn something that we didn't know before the process started. So, what a titration involves is a piece of glassware called a burette. Okay, and burette is spelled like this: Burete. Okay, it involves a burette, and inside that burette we have what's known as the titrant. Okay, now the titrant is either going to be an acid or a base. All right, the opposite will be down here. Okay, so let's stick up here though for a second. Let's say our titrant is an acid. All right, whatever is inside our burette, whatever the titrant is, all right, we know the molarity. All right, down here, the thing that we're analyzing, we call it the analyte. And before the experiment starts, we do not know the molarity of the analyte. So now we can kind of see the purpose of a titration. We have something with a known molarity. And what we're going to do is we're going to run a reaction and we're going to track how far that reaction is progressing. All right. At the end of the process, we're going to be able to take this original sample, right, the analyte, and we're going to be able to decide something that we didn't know before. We're going to be able to figure out its molarity, how many moles there were in this original liters of solution. Okay, so then here's how it works. You add the titrant drop by drop. You add until an end point is reached, right? So the whole experiment stops when the moles of acid and the moles of base in your neutralization are equal to each other. So it really just sort of stops as soon as everything is completely neutralized. Well, how do you know when that neutralization has occurred? All right, so you can't really go down and see the molecules yourself. Well, inside this analyte, we also add an indicator. And what an indicator does is it changes color when you switch from acid to base behavior. Okay, so I'm just going to do a quick little example, but it's all kind of about understanding that when you get a problem, you'll see words like endpoint, titrant, analyte, all right? And it's really just trying to, really just understanding it's not a limiting reactant problem because you know that if the endpoint is reached, the moles of acid and the moles of base were equal to each other. Both the H plus and the OH minus are limiting reactants. They both are, and you know that in a titration. And you'll see this with this little cartoon that I draw. So let's imagine that we have H plus down here to start with. And I'm just going to draw 3 different H pluses. Okay. Now, there's a certain initial volume that I'm trying to analyze. And only that initial volume matters, right? And the H pluses are floating in that volume. And so there's a certain concentration. Now, I don't know what that concentration is, but if I know the concentration of my titrant up here, which would be OH minus, right? What I'm going to do is I'm going to monitor the volume of this that's added. And from a previous lecture, okay, if you know volume, right, and if you know molarity, what do you know? You know moles, okay? So I'm essentially going to monitor this reaction with a known molarity and volume, all right? And what I'll see is, oh, well, I'll be able to understand how many moles of base I've added. Well, I'm running a reaction then that will tell me how many moles of acid were in there to start with, right? If I have a moles of acid and a volume of acid, I can get a concentration, right? So if I take this burette and I start putting in OH minus, how many OH minuses do I have to add, okay? And essentially I can drop in 1 OH minus and I make a water, an HOH. I put in another OH minus, I make another HOH. I put in another OH minus, I make another HOH. And then I put in another OH minus and there's no more, all right, acid for it to react to. And there's also an indicator in there. And that's the point that the indicator would change color. And it would say, hold on a second, your previous drop of OH minus, that's when the moles of base were equal to the moles of acid, right? So this is just a general idea of how a titration works, right? Unfortunately, you won't be able to enact one yourself in the laboratory this summer, but you do need to know how to interpret problems. And again, I'm going to focus in on the big important parts. It's not a limiting reactant problem, okay? Even though a reaction is occurring, you know one thing and you infer the other thing based off of what you know, right? So what I want you to do is take a look at slide 6 on our chapter 4 PowerPoint. And what you'll see is a setup for an acid-base titration. Now that acid-base titration involves HCl, right, and NaOH. So that is the reaction that's being run. Well, we know that if I have HCl aqueous and NaOH aqueous, that the reaction that occurs is, okay, switch to positive things. I get NaCl. I look at my solubility rules, that is aqueous. And I get HOH, which I know is H2O liquid. Okay. So the acid-base neutralization for this particular example is shown right now. And we look to balance it, but it's already balanced. So we're set and we're ready to go. Okay. We know now, all right, based off the information that's given, a molarity of NaOH, which is given as 0.1524 molar. And then there's wording in the problem that tells you that the volume of NaOH used to get the endpoint, right, was total 33.32 milliliters. Okay, so when I was drawing that little picture in the last, at the beginning of this video, okay, remember how I said one of the species will have a molarity and volume that we know? In this case, it's NaOH, okay? So NaOH is our titrant, right? If I know molarity and volume, I know moles of NaOH. There's a sample of HCl that you're supposed to analyze, all right? And you're supposed to determine the unknown molarity, right? Now, the sample that you're supposed to analyze has a volume of 0.05000 liters. And I converted the milliliters to liters already, okay? And we'll see why when we get to the end. We're going to determine a molarity, and what's in the bottom of molarity, it is liters of solution. So, okay, to that point, right, if I want to get the molarity of HCl, what I need is the moles of HCl and the liters of solution. And one of those values I now have already. I have this denominator because I know the original volume that's being analyzed. I know that amount. So the whole entire process now is about determining the moles of HCl that must have been in there to start. Well, based off the stoichiometry here, right, and stoichiometry does matter, okay? So you go and you look at your stoichiometry and you say, okay, well, if I know molarity and volume, I know moles of NaOH. If I know moles of NaOH, I know moles of HCl. Now, this is a simple case where there's a 1-to-1 ratio, and that's not always the case, right? So what I'm going to show you, because you can kind of infer what you have to do even now probably, I'm going to show you just a full method of attacking this, okay? We're going to get to moles. All this will sound familiar. We're going to get to moles, we're going to bridge over, and then we're going to finalize our question from there, finalize the answer to this question. So I'm going to start with 33.32 milliliters of my NaOH solution. I'm going to convert that to liters. There's 1,000 milliliters in 1 liter. Now I can use my molarity, and it's 0.1524. Remember what big M turns into? Moles of NaOH per liter of solution. And now I look at my balanced reaction. 1 mole of NaOH is equal to 1 mole of HCl. So I can put this into my calculator. I get 5.077968 times 10 to the minus 3 moles of HCl. Okay, so this is all about just understanding the equivalency, being able to use this stoichiometric reaction, stoichiometrically balanced reaction, to take information about one species with a known molarity and volume and convert it to information about the other species. I can come back up here to my molarity now, and my molarity is 5.077, right, 968 times 10 to the minus 3 moles of HCl in my original sample, which was 0.05000 liters of solution. Let's keep track of significant figures here. 4 here, 4 here. These two are exact, so this should have 4 significant figures. This should have 4 significant figures. This has 4 significant figures. So my final answer has 4 significant figures. And what you get is 0.1016 molar. Okay? So it's another recognition thing. When you see a word like titration, when you see endpoint, when you see analyte and titrant, just tell yourself what you look for is a known molarity and volume to give you a known moles. That's exactly what we did with this conversion here. Our molarity and our volume gave us moles of NaOH. You then use your balanced reaction to take the moles of the things that you know and convert them to the moles of the things that you don't know. That is going to be an unknown that will be divided by a liter of sample, right? To take the moles and turn it into a molarity, all right? So just make sure, as always, this makes sense, and if not, contact me. This ends chapter 4. There's a lot of important things here, a lot of really practical skills and things that we'll use even in subsequent chapters. So it's really important that you master as much as you can. As always, reach out to me if you need any help at all.